Okay, this section 4.1 is about transforming relationships. And essentially, what it's doing is taking nonlinear data and making it linear so we can run regression analysis on it. Your calculator, nowadays, calculators can do this without, but it was very, very difficult to do this without by hand. And in a lot of cases, the transformed data is a lot easier to see the patterns in. Okay, so looking at this data, we got this big cluster kind of in the lower portion here down here. It's hard to tell what, if any, patterns are there. And then we have these four kind of outliers slash influential observations. And this is body weight on the x-axis versus brain weight. Humans and dolphins have large brains for their body weight. Hippos and hippos have small, it looks like. Elephants just have big of both. So we're going to talk about transforming that. And how we transform these data is we take the logarithm of all the x data or all the y data or both, usually the logarithm. We can do other things to it. So this is zoomed in, and it looks like we might have a pattern that looks a little bit more logarithmic. It's a little bit more like this. That looks like a logarithm graph. So, or maybe a square root graph. If we take the logarithm of both axes, even with the outer points, logarithms condense everything in, we get what looks like reasonably linear data. And we can talk about residual plots, okay, etc. So when we're talking about data, that becomes very important. So monotonic functions means it's moving in one direction. So as one increases, the other always increases, or it always decreases. Monotonic increasing preserves the order when you do a transformation. Monotonic decreasing reverses the order. So if A is greater than B and it's decreasing, when I apply most of these functions to it, f of A becomes smaller than f of B. And we've seen graphs that look kind of like this. This is essentially linear positive is y equals x. The square is y equals x squared. The logarithm is y equals log x. Y equals negative x. Y equals 1 over square root of x. And reciprocal y equals 1 over x. Those are four. The top ones are monotonic increasing. The bottom ones are monotonic decreasing. But all of these are headed in only one direction. So the ladder power of transformations, you've seen this in pre-calc. In pre-calc, we looked at it more like this. And we had this one coming across like that. Similar effect here. We're not going to focus on that. I'm not going to test you on that. So here we have a graph of gross domestic product versus life expectancy for countries. Notice they didn't put the bottom at 0. And it looks like it's kind of a logarithmic or square root graph. Except kind of those 3 points, which kind of look funky on a lot of them. If we square root the x-axis, we get something closer, not quite. We get an R of 0.82 now. If we log the x-axis, we get something pretty good. If we go 1 divided by the square root of gross domestic product, this actually reverses the order when we start dividing. And that is kind of an interesting. We get a slightly higher R. I would tend to move towards this would be my choice, even though the one fits the line better because it's less of a screwy transformation, reversing order, and all kinds of things that don't make a ton of sense. So that's a little bit of the theory behind this. You guys know what exponential growth is. You know what linear growth is. So we're going to talk about how to do this, how to actually apply this to a problem. A dollar invested at an annual rate of 6% returns 1.06 in a year. The following dollar remain has earned 6% interest, that is 6% annual interest, multiplied by 1.06 every year. The new amount is therefore multiplied by 1.06. This is not only 1.12, but in turn is multiplied by 1.06 the third year. So, if the Native Americans who sold Manhattan Island for $24 in 1626 had deposited that $24 in the savings account at 6% annual interest, good luck finding that. They would have now had almost $80 billion. Their 24 would have turned into 80 billion. Our savings account don't make us billionaires because we don't live long enough. $24 was also quite a good sum of money back in 1626 versus now it's like, hey, you want to pay me that for the last hour of work? So a century of growth at 6% turns 24 into 8,143, which is a great, great gain, but that's 100 years. By 2 centuries, would have been about 27 million. Only after the 302 years do we finally reach a billion. That's real money, but 302 years is definitely a long time. So, exponential growth model. So here we've got the growth of cell phone use. Does our exponential model sometimes describe real data? Yes. So here we've got cell phones and the number of subscribers from 1990 to 1999. This was before cell phones were real big, but they were starting to catch up. There's an increasing trend, but it does not look linear. In fact, it's curving up. It's probably exponential. So what we're going to do is we're going to do a logarithm transformation. And the first thing I'm going to do here is I'm going to take all this data and I'm going to put it in my calculator. And I want to see what they did use 1990. So I go to my calculator, and like any regression from pre-calc, I do a new one. I don't need anything that I had. So I do a listen spreadsheet, year, wrong year there at the end. And I'm gonna grab a book here so I can actually look at the data, make it easier. You type. So here, oh, there's my data. Cell phones. Okay, so here we've got our cell phones and our years. And to transform it, what I'm going to do is I'm going to take the logarithm, or the natural log, because it's the easiest one, of, well, the book does the log base 10. So to do that, I'm going to call it log cell. And in this column, this is the formula column. I'm just going to do the log base 10 of, and I'm just going to type cell in here, and that'll take that whole column. Now it has linearized that. And so I'm going to take and I'll add a page, a data and statistics graph. And I'm going to do year versus log cell. And I see that I'm going real straight and then a different straight. And so that's kind of a little bit of an interesting, somewhat screwy thing. So I'm going to actually get rid of, if I do the whole thing, I can make a linear equation. I can do a linear regression here. Menu. Let's just do my linear regression. Analyze regressions, show linear. So now I've got my linear regression. Remember, it's always a good idea to look at my residual plots. And I'm blanking on showing the residual. Oh, residuals, show residual plots. I have a pattern. I definitely have a pattern here. So I probably need to do something differently. And what probably happened is the trend changed here in 1996. So what I'm going to do is I'm going to go back to my data, and I'm just going to get rid of my data before 1996. And it seems to keep it. I now have a different equation. So I have an equation for what I do not have is y versus x. I have an equation for log y equals negative 188.95 plus 0.0969. Yeah, I'm gonna keep that many. So if I want y, the way to get y is to raise both sides to the power of 10. And that's the entirety of this whole side. It's like there's parentheses around there. 10 to the log y is a nice little number, nice little variable called y. When I add the exponents, it's like multiplying them by like bases. I don't want to even think about what 10 to the negative 188.95 is. Very small number. This can be isolated like that. And I need to get a calculator for this. This 10 to the negative 188.95. Really small number. Move the decimal a lot of places. This 10 to the 0.0699 is 1.25. And this is a prediction that I can use for my cell phone growth. Important pieces of this are that as my cell phone use grows, I don't want to predict too far into the future. That would be extrapolating, can become very dangerous, and I can way, way, way go beyond what I think I need. Okay? So that's my cell phone growth. Just need to look at something. I need to see if I'm actually supposed to leave off here or if I just didn't plan well. Okay? We're going to leave off there. That is kind of a key thing, and we will pick up with this on Monday. Or in the next lesson, depending on which